The pitch, dynamic route optimization. Hi everyone. Today, I want to talk about the biggest headache in logistics, the last mile delivery. Now, we already know it's the most expensive part of the supply chain. But as companies finally trade in their gas engines for electric vehicles, we're hitting a brand new wall: range anxiety. The problem is that traditional GPS doesn't understand EVs. It doesn't care about how a steep hill, a heavy load of packages, or a cold morning can absolutely tank a battery's charge. This is exactly where machine learning comes in. We have a massive opportunity to move past simple point A to point B routing and transition into what I call energy-aware optimization. To see why this is a perfect fit for an AI solution, we look at three things. First, the complexity. Imagine trying to balance 50 different stops, real-time traffic, and the way a battery drains, which isn't a straight line, by the way. It's way too much for a human dispatcher to calculate in their head. Second, the scale. We aren't just talking about one van, logistics hubs are managing hundreds of them at once. We need a system that thinks about the efficiency of the entire fleet, not just one driver. And finally, the data. These vans are basically data gold mines. They are already equipped with telematics that track GPS, speed, and battery levels every few seconds. We have the information, we just need the intelligence to use it. By combining these three factors, we can finally take the guesswork out of electric delivery. The strategy, success, and metrics. So, how do we define a win for this project? Our primary goal is simple: we want to squeeze the maximum number of deliveries out of every single charge while making sure we have zero stranded vehicles. No one wants to send a tow truck for a dead van. To know if we're actually succeeding, we're going to track two different types of numbers. First, there's the business outcome. We're looking at the kilowatt-hour per delivery, basically, how much energy does each package cost us? And of course, we have to maintain our on-time delivery rate. Efficiency doesn't matter if the customer gets their package late. Second, we have our technical output. This is where the machine learning comes in. We'll be measuring the mean absolute error of our battery drain predictions. Put simply, if we can't accurately predict how fast a battery will die, we can't safely optimize the route. Our math has to be spot on. Now, to get that accuracy, our model has to account for the real world. We're looking at four crucial factors. Payload weight, because a heavy van is a thirsty van. Elevation, hills are battery killers. Temperature, because cold weather changes the chemistry of the battery itself. And finally, traffic. In a gas car, traffic just wastes time. In an EV, stop-and-go driving actually changes how regenerative braking performs. By feeding all of these variables into our model, we move from guessing to precision. The solution, validation and testing. Now, how do we actually build and prove this works? Our core approach is going to use reinforcement learning. Think of it like this: we're going to let our model practice by simulating millions of delivery days in a virtual environment. It learns by trial and error, finding the most energy-efficient paths before we ever put a van on the road. But we aren't just going to trust the simulation. We have a three-step validation plan to make sure this is ready for the real world. Step 1 is backtesting. We're going to take historical data from the last year and run a what-if scenario. We'll ask, if our AI had planned these exact routes last year, how much energy would we have saved compared to what actually happened? This gives us our baseline. Step 2 is our A/B fleet test. We're going to run a 1-week pilot program. We'll split a hub into two groups. Group A keeps using the standard routes, while Group B uses our ML-optimized routes. At the end of every shift, we're going to check the battery levels. The win here is seeing Group B return with significantly more charge left in the tank. Finally, and this is crucial, we need driver feedback. A route might look perfect on a computer screen, but if it includes a dangerous left turn or a road that's impossible for a large van to maneuver, it's not a good route. We need that a human-in-the-loop validation to make sure these paths are not just efficient, but realistic for the people actually doing the work. In the end, it's about merging the best of machine learning with the real-world experience of our drivers. The system architecture. Now, let's talk about the brain behind the operation. When we sat down to design the ML system, we had to make 3 key architectural decisions to ensure this actually works in the field. First, we're going with a cloud-based architecture. Now, you might wonder why we aren't doing the processing on the vans themselves. The reason is simple: to optimize a fleet, you need a bird's-eye view. You need to see every van, every traffic jam, and every charging station all at once. By using central servers, we can handle the heavy math required to coordinate hundreds of vehicles simultaneously. Second, we've decided on online learning. In the world of logistics, a model that only updates once a month is useless. Road conditions, construction, and traffic patterns change by the hour. By using an incremental, online approach, our model is constantly learning and updating its understanding of energy costs as the data flows in real time. And finally, our system operates on a request-response basis. We can't rely on batch processing where routes are only calculated once a morning. Why? Because the real world is unpredictable. If a driver hits an unexpected road closure or a sudden storm, they can't wait until tomorrow for a new plan. They need a new, energy-optimized route right then and there. This ensures our drivers are never flying blind. By making these choices, we're building a system that isn't just smart, but is also responsive and scalable. Managing risks and the final goal. Now, I want to be realistic. Moving a system like this into production comes with its own set of risks, and we have to be prepared for them. First, there's the risk of training serving skew. Imagine we train our model using data from the summer when the vans are mostly empty. If we then deploy that model during the holiday rush, when every van is packed to the roof with heavy boxes, the AI is going to underestimate how fast that battery will drain. We have to ensure our training data matches the seasonal reality of the business. Second, we have to account for concept drift. Specifically, the fact that EV batteries degrade over time. A 100% charge in a 3-year-old van won't get you nearly as far as a brand new one. Our model can't be static, it has to adapt to the aging of our fleet, or its predictions will slowly drift away from reality. And finally, there's latency. In last-mile delivery, seconds literally matter. If our cloud system takes 10 seconds to calculate a new route, the driver has probably already missed their turn. That leads to wasted energy and, frankly, frustrated customers. Our tech has to be fast enough to keep up with the pace of the road. Conclusion. To wrap things up, by combining EV technology with machine learning, we're doing more than just delivering packages faster. We're delivering them sustainably. This project is proof that our business efficiency and our environmental goals don't have to be at odds, they can actually go hand in hand. When we optimize for the battery, we optimize for the planet. Thank you.